Good morning, everyone. Today we are going to continue our talk about the phase diagrams. You can see this is our fifth class session for phase diagrams. You can see how important the phase diagrams are. And here today's objective, we want to learn iron-carbon phase diagram. This is the one of the most important topics in material science because iron-carbon um, are commonly used for industry applications. First, we want to refresh your memory about these three important reactions: and eutectic, eutectoid, and pereutectic. Eutectic means that we have these changes from one liquid phase. But if we cool it, we will have two solid phases, alpha and beta. And however, for this alpha beta, if we heat alpha and beta at some temperature, we can get this liquid phase. It's a four-lead tin phase diagram, and there is one eutectic point, which corresponds to 183 degrees C, along with 61.9 weight percent of tin. So this is eutectic. Be very, very careful about this eutectic. And second one is eutectoid. One solid phase transforms to two other solid phases. So this is the equation can be written as S2 and goes to S1 plus S3, and also this is for cooling and then heating S1 plus 3, we will get this S2. And one example is this gamma iron. When we cool it, we can get this gamma alpha, iron alpha plus this compound. It is an intermetallic compound and cementite. This is cementite. If these two guys, if we heat it, we can get this gamma. The third one is pereutectic. Pereutectic is liquid and one solid phase transformed into a second solid phase. And also this is the general equation, and here is a specific example, still for iron-carbon phase diagram. At the pereutectic point, which corresponds to 493 degrees C and 0.16 weight percent of carbon, and we can have this is pereutectic. As you can see, delta plus L, and delta plus L, and we can have gamma, one solid phase. So these are three very, very important concepts I want you to know, to keep in mind, to memorize all these three chemical equations very, very clearly, and you should be able to use your own words to tell people what these three concepts are. And then for this our first phase diagram for this is a copper zinc phase diagram. So here is the phase diagram. This is a combination, so this is temperature. We can have, this is a gamma, gamma plus epsilon plus L. Here is L, gamma L, this is delta plus L, this gamma plus delta, this delta. So here is one specific point E there, and to this point will be eutectoid transformation. And why? Because we can have delta for this. If we lower the temperature, so the phase, the material can become from one single solid phase, this delta, into this gamma plus epsilon. Based on the definition of eutectoid, we know this point is eutectoid, the eutectoid point. So here, this point, this is a pereutectic transformation. Why? Because um, because it follows the peritactic transformation definition, you can see if we at this point, if we lower temperature, we can have gamma plus L, and then we will get this delta, one single solid phase delta. So be very, very careful in our upcoming quiz or this is the exam. I might give you this phase diagram, and then I will ask you to tell me to label which point is peritactic, which point is eutectoid. And you should be able to tell me and then tell me why. Right? Any questions so far regarding this slide? No, we talk about this is, as I said, most important phase diagram for this material science class. It is called iron carbide phase diagram, or it is called iron carbon phase diagram. And so this is why this one is the most important, because the iron, and also if we have iron plus carbon, we have steel, and this is material, these kind of materials, and they are commonly used for industrial applications. So this is very, very important. You can see, okay, I can see here, this is a degree 727 degree C. You can have here, right? And so here is a 0, this is a 6.70. And so from there to here, and so here is a liquid, and this is a gamma plus liquid. And so here is austenite, this austenite. And here is the heaviest temperature, 1538 degrees C here. And so this is 1493 degrees C here. So here is the delta, and this degree is here. All right. And so here is a 12 degrees C. In this area is alpha plus gamma. Gamma is austenite. And here is a ferrite. This is alpha ferrite. And this is cementite. Cementite is a intermetallic compound, Fe3C. So this is the alpha plus Fe3C, and this gamma plus Fe3C. Some students might ask, Donna, what about the composition beyond 6.70? So beyond 6.70, we will not call this guy as a steel. We call it as a graphite. All right. So this we will talk about this one later. Any questions regarding this phase diagram? So first we talk iron carbon phase diagram, or this iron carbide phase diagram. And so here is two important points here. And can somebody tell me what is this one? What is this one? And what about this one? So this is one gamma. One gamma. If we lower temperature, and this is a solid gamma, becomes two solid other two phases. So this is called eutectoid. And what about here? So this is this point. If we lower temperature, the material becomes the material transforms from the liquid phase to gamma plus Fe3C cementite. Eutectic point A is eutectic point A, and this is eutectoid point B. So this is two important points, and I will ask you guys to tell me what for this diagram what this point is called, and what this point is called, how they are different, and how they are so important, and what are the characteristics for these 2 points. So you can see here, right? So here these are gamma greens, these are green boundaries here. And however, if we go down, we will have cementite alpha ferrite, right? So we have alpha ferrite, and it is softer, but we have cementite hard, which is hard. And so this is cementite lamella here. So here is a micrograph of this pearlite. This pearlite is alternating layers of this ferrite oliver and this is cementite, the physics. So here this is pearlite. I want you to know this is the very important. You can see in this slide there are so many important concepts. Eutectic eutectoid, eutectoid point. So this is a pearlite, and so this is austenite, and this is a pearlite austenite, and this oliver is a ferrite, and so this is a cementite. Any questions so far? These are photo micrographs. So this alpha ferrite and this delta ferrite and have a BCC crystal structure. Alpha is relatively soft and may be made magnetic at temperature below 768 degrees C and has density of 7.88 gram per centimeter cubic. So you should know that, okay? So this one BCC, not BBC. I'm sorry, this is my fault. Austenite has FCC crystal structure. It's non-magnetic, and you should know alpha is can be made magnetic. So this is a very important application for this alpha ferrite. So cementite is very important concept. It is intermetallic carbates, intermetallic compound of here the carbates. Cementite forms when the solubility limit of carbon in alpha ferrite is exceeded at below 723 degrees C. Right? So this is cementite. Cementite also coexists with alpha phase between 723 and 1473 degrees C. So mechanically, cementite is very hard and brittle. The strength of some steel is greatly enhanced by its presence. And so be very careful about this cementite. And then we talk about eutectic and eutectoid reactions for this specific carbon and this cementite phase diagram. So here is a eutectic and this eutectoid. Okay, eutectic L go to gamma plus this cementite, and eutectoid, and with also here is composition is written gamma, and get this alpha and this cementite. And I want you to know and at what condition this happens, and what also the percentage, the composition of each of these guys. And you should know that specifically for this carbon and this iron and iron carbide phase diagram. So development of microstructure, we want to talk about this. So here is a eutectoid point here, right? This eutectoid. So here is a pearlite. I told you this is a pearlite, alternating layers of alpha ferrite and cementite. We call pearlite. And here, above this temperature, we have this austenite, gamma austenite, and we have polycrystalline austenite. You can see this is gamma greens, and this is the green boundaries. And so here is the photomicrograph of eutectoid steel showing the pearlite microstructure consisting of alternating layers of alpha ferrite, and this light phase, along with this is the cementite, and thin layer, cementite thin layer, most of which appear dark, And so this is the is from Mato's handbook here. So this is development of microstructure. So this so here, okay, so here is austenite. You can see this austenite, and here is the growth direction of pearlite, and here is these two layers. Right, these are two layers, and so this is the austenite boundary. This is cementite. So this is a carbon diffusion. As you can see, the carbon alpha has very low carbon, and cementite has relatively high carbon. The carbon diffuses um, in this direction, as shown by these arrows here. So this is a growth of the direction of the pearlite. Any questions regarding this slide? And then we talk about hypereutectoid steel. And in last slide class, we talked about this one. Okay, so this the hypo and hyper. And hypo means that the combination is lower than the combination at this eutectoid point. And so for here, it is this, right? So this from here to the left of this point, we have hypoeutectoid steel. And you can see here, and just show you, here it is this gamma austenite grains boundaries. And here, we will have some pieces of tiny circles here, and tiny circle is this tiny circle actually is this is alpha plus IV3C. So here you can see this is alpha, this is gamma. So this alpha is growing here. I'm sorry, this is gamma. Okay, gamma plus cementite. This is I'm sorry here. So this is the alpha here. Right, this is alpha. We go down, and so here is alpha. So this is the big alpha, and so you can see other layers of alpha, and so this is called the pearlite. So for this one, and this pearlite embedded with this larger, this is primary alpha. And so micrograph shows this as shown as this one. So this is pearlite. So this is pearlite. So this is a pro-eutectoid ferrite. We call this larger one, white one here. Here it corresponds this one. It's pro-eutectoid ferrite. If I give you this micrograph, if I ask you guys to label these different phases, can you guys do that? Okay, I hope you can do that. Okay. Next slide. And we can calculate, and this is the weight percentage, and this is the weight percentage. And so this is alpha and gamma, and here we're using this as a level rule. We draw a tight line horizontally, and then have these 2 points, and use this equation to get weight percentage of alpha phase and weight percentage of this gamma austenite phase. So here this point, we draw a horizontal line also. This is the R and S. You can see this S is so high. That means this guy's with the percentage is much higher, this part. And this is W pearlite, and this one S so high, and W alpha prime equals S divided by alpha, R plus alpha, and with the percent of the cementite equals 1 minus this one, right? So this is another way to calculate. Questions? No question? We talk about hypo. Now we talk about hyper. Hyper means that the combination is higher than the eutectoid combination. As for to be specific for this one, so this is a this is the eutectoid, the percentage composition. That means all the compositions that are higher than this one, we call this is hypereutectoid still. So here is a gamma, and this is a boundary, and we have this dot here, and this dot is gamma. Right? For here, the dot is alpha, but here is dot is gamma. So when we go down, the gamma grows here. You can see the gamma grows like bigger branches here. And then come here, and we have pearlite, but this time, and we have this is the bigger branches are spreading in this pearlite. So this is one is called. This is the cementite. This is the cementite here. And so we want to do this is the weight percentage calculation, and we use the same rule, level rule here. So you can use this equation to calculate. The gamma is x, right? Numerator is x. We need to be very, very careful. For this point, we have pearlite along with this is the branches of this is a gamma. At this point, we draw a vertical line. This is v and x. We can use these equations to get the percentage of this cementite, the percentage of this pearlite, and the percentage of this alpha. So this is the so this is micrograph. We have pearlite, and we have these bigger branches. They are cementite, right? So these are cementite. So example problems. So for example, for a 99.6 weight percent iron and to 0.40 weight percent of carbon steel at a temperature just below the eutectoid, determine the following: the composition of cementite and ferrite alpha, the amount of cementite in grams that form in 100 gram of steel, and the amount of pearlite and per eutectoid ferrite in the 100 grams. And the solution you can see here. We use the RS line just below the eutectoid. Right, so this draw a line here. We can get this is alpha, and this is a C cementite, using this draw line here. Right? Using a level rule with the tie line shown, and this is this one equals the weight percentage of cementite equals R, so this R, divided by R plus S, get this number, and amount of cementite in 100% and equals 100, this one multiplied by this percentage, you can get this one, right? So this is very straightforward. And third one is using the Vx tie line just above the eutectoid and realize that Vx. And C0, C alpha, and C pearlite, you can get these. C pearlite can be obtained using this equation. Amount of pearlite in 100 gram equals this 100 total mass multiplied by the weight percent equals this one. And then we talk about alloying with other elements. Eutectoid changes. Okay, so this is the weight percentage of alloying elements. So this is the eutectoid temperature. So we can see that by using different alloying elements, we can artificially change, we can effectively change. And so this is eutectoid temperature. So this one That means we can, based on our needs, we can using different alloying elements in order to get desired eutectoid temperature. So this one is very, very important. So you can see we have nickel here, right? So it's a nickel and manganese, chrome. So this is the silicon. So this tungsten, this molybdenum, and this is titanium. For different, you can see for Ti, okay, for example, Ti, if I have different Ti percentage, I can drastically change the eutectoid temperature. And on the contrary, for nickel, and I can increase the nickel's composition and to lower the eutectoid temperature. And so you chrome, right? Chrome you can also, you can just use different the chrome percentage of chrome and to change the eutectoid temperature. And so these are very, very important alloying elements, and they can give us a lot of convenience. And because eutectoid temperature is very, very important. Why it is important? Because we can lower the temperature or enhance the temperature to do something that are special for our needs. And I will talk about this one in detail later. Any questions so far? And then we talk about this is the composition of eutectoid changes. So you can see titanium, molybdenum, tungsten, silicon, manganese, chrome, and nickel. So if we alloying this guy, and for example, for nickel, if we increase the composition of nickel, percentage of nickel, we can drastically change the eutectoid composition. You can see from here to here, change this one, and so this is we just change from 0.7879 and to 0.2. So you can, that means by using different alloying elements, and you can achieve your goal. Which means that you can alter the eutectoid temperature, and you can alter the eutectoid composition. And so this is very, very important for this is the iron and iron carbide phase diagram. As I said, this is the most important topic in the material science because in our industrial applications, almost 90% of this is engineering applications, and we use steel. I hope and you understand these slides very, very well, very, very clearly, so you can get very good grade for this is the upcoming exam, and finally, and you can apply this knowledge, apply these skills in industry when you get a job. Thank you very much for your attention. I will see you this Friday.